In this video, we will understand what is diffusion current. Before we even go into the current part of the diffusion itself is a very important natural phenomenon that happens almost every day in our life. So let me take an example to understand this diffusion process. So let's say we have a chamber in which we can place some wood and put it to fire. So let's say I'm putting this wood to fire, and we have, let's say, a chimney, the outlet to this chamber, to allow the smoke to go out. So now when the wood is burning, we will have smoke coming out of it, and it will be going through this chimney. And now when it is coming out, it tries to spread around because the concentration of this smoke particles is higher at the outlet of the chimney, and the smoke particle concentration in the environment is far less compared to the concentration at the outlet of chimney. As a result, the smoke particles would tend to actually diffuse themselves into the environment. So that's why we see the smoke actually going outwards. And this process with which it actually goes from higher concentration to lower concentration is called diffusion. So now the same kind of phenomenon is present in our semiconductors, and we have a current associated with it. That's what we're going to discuss now. So let me take electron concentration in the y-axis and the distance on x-axis. Let me say the electron concentration is changing with respect to space like this. In this case, we can see that the carrier concentration at this point is higher compared to the carrier concentration at this point. Let's say this is point A and this is point B. Now the carriers at point A will have the tendency to diffuse to the lower concentration side. As a result, these electrons would try to flow towards the B side. Because the carriers are flowing, now we know these carriers have associated charge with it. So which means the charge is actually flowing. When charge is flowing with respect to time, then we have some current. And that current is called the diffusion current. So in order to start with, I'm going to discuss diffusion current density, which is represented with J. And as we are saying diffusion, and that too in this case we are talking about diffusion current of electrons. So I'm going to say this Jn diffusion. This is diffusion current. Now the rate of flow of these carriers from higher concentration to lower concentration would be dictated by the concentration gradient, which means the concentration change with respect to distance. So let me take another example where the carrier concentration is pretty much like this. In this case, there is no change in the carrier concentration. Let's say this is a point A dash, this is point B dash. Now the carriers at A dash would not see any reason why they should be moving towards B, because there is no concentration variation from A to B, and in the middle as well. So the carrier concentration gradient is the one which actually drives the rate of flow of these carriers. So which contributes or gives rise to a current which we are calling diffusion current. So we are defining this Jn diffusion, which will be directly proportional to the variation of the charge with respect to distance. And we have a mathematical formula to represent this, which is differentiation of this, which means the variation is captured in the slope of this function, and differentiation basically gives us the slope of the function. Now it's not just the carrier concentration gradient, it's actually the charge gradient, because it's the charge that actually flows which gives rise to current. So we are multiplying this with a Q. And another point is, when the carriers are flowing in this direction, our current is actually flowing in the opposite direction. When carriers are flowing in this direction because of the concentration gradient, our current actually flows in the opposite direction, because the current flow, the conventional current flow, is in the opposite direction to that of the electron flow. So we're talking about electrons here. So the current is flowing in the other direction. Now if you observe, the differentiation of this function would be negative, which means dn by dx would give a negative value, which indicates that the current flow is actually a negative direction. In fact, a point to mention, the current density is actually a vector function. Not to complicate stuff here, I'm simply not mentioning it as a vector. I'm just trying to find the value of it. So which means the differentiation basically captures the direction of the current density as well. as it is directly proportional to, we're going to take a proportionality constant which will be equal to, I'm going to call this d suffix n, which is called the diffusion coefficient of electrons. So we have the other terms, which is q times dn over dx. Now this is the diffusion current density of electrons. And this diffusion current is primarily driven by the carrier concentration gradient. In general, n might not be just a function of x, the space. It can be a function of time sometimes, which means n is a multivariable function. So in that case, we cannot directly mention the differentiation. Instead, we should be writing this in terms of partial differentiation. So let me write this here, q dn del n by del x. And similarly, if you're interested in finding the current itself, the relationship between current to current density is I is equal to J times the cross-sectional area. Usually, J is a vector quantity times area is also a vector quantity, and current will be a scalar quantity. So what does this area mean? Let's say I'm taking a piece of semiconductor here. If you're measuring the carrier concentration gradient in this direction, then the area that we're looking at is this cross-section area. So we can write the current for n diffusion, which would be equal to q times a cross-sectional area times dn times del n by del x. These are very important equations to remember. Now let us see diffusion current for holes. I'm taking the hole concentration on y-axis and the distance on x-axis, where I'm taking the similar kind of distribution of holes with respect to space. So where p is a function of x. In this case, at point A, the carrier concentration is higher compared to carrier concentration here, which means there is a carrier concentration variation or gradient which will drive the natural process called diffusion. In that case, holes would be moving in this direction. But if you see, the current will also be in this direction because positive charge moving direction is actually the current direction as well. So similarly, as we defined in electron diffusion current, we're defining here Jp diffusion, indicating this is diffusion current density for holes, indicating that this is diffusion current density for holes, which will be directly proportional to Q times the concentration gradient of the holes. But now, let us see. The dP by dx, the differentiation of hole concentration, would be negative. But in fact, the current is actually in the opposite direction to that of the value of dP by dx. So in order to correct this, we will multiply this with a minus sign. So that multiplying this with minus 1 would give this one. So that's why Jp diffusion is directly proportional to minus q times dP by dx. Now we can take the proportionality constant here. Jp diffusion is equal to minus q the d suffix p times dP by dx, where dP is the diffusion constant of holes. So now p can be a function of space and time sometimes. So as a result, we can generically write this as Jp diffusion is equal to minus q dP del p by del x. And if you are interested in current, then we can write this as Ip diffusion is equal to minus q times the cross-sectional area times dP times del p over del x. This is a very important expression. Let me write down both the expression we derived. Now we don't know the units of dP and dn. So let us find from this equation. Now I'm picking Jn diffusion equation to find the units. We know that current density is basically amperes per unit area, which I'm taking centimeter square, let's say, which is equal to, we have Q here, coulombs, times something which we don't know the units of, times del n by del x. We know the n units is number per centimeter cube, which is carrier concentration. So I'm writing 1 over centimeter cube times we have 1 over del x, del n by del x. So we have 1 over centimeter distance, dx distance. So now we can find the units of this particular term. So centimeter square cancels 2 of this out of 3. Then we have amperes is equal to coulombs over centimeter square. times the one which we are trying to find. Now amperes is nothing but coulomb per unit time, which we're writing seconds. So we have coulomb per centimeter square times the units to find. Coulomb cancel. So the value that we're trying to find, which is the units of the diffusion coefficient, which is equal to centimeter square per second. A very important point to remember that diffusion current doesn't depend on electric field. We have never considered electric field in this case. It depends on carrier concentration gradient.